Okay, just like in the case of conjugated dienes, molecular orbital theory gives us a good explanation for the structure and bonding of benzene. Okay, so just to refresh your memory, despite the original theory that the two potential structures of benzene, the two Kekulé structures, are equilibria, they are not equilibria at all. They can be explained using structures 1 and 2 as resonance structures, but structure 3 here is another structure that you will see very frequently, where you just take a circle and put it inside the hexagon, and that represents the partial double bonds between all 6 atoms and does not suggest that the double bonds are localized between any 2 particular carbon atoms. So once we get into this whole idea that pi bonds are delocalized over an entire structure, the most appropriate description to use for this is a molecular orbital description. Okay, so what are we going to do? Well, we're going to treat benzene the same way we treated the conjugated dienes, and we said that we will use valence bond theory to explain the sigma bonding. And we're only going to use MO theory to explain the pi bonding. So we will have a planar structure where all of the hydrogen-carbon-hydrogen bond angles, hydrogen-carbon-carbon bond angles are 120 degrees. And then all of the carbons are sp2 hybridized. So if they are sp2 hybridized, that leaves one p orbital available for overlap with the p orbitals on the neighboring carbons, and allows us to form 6 pi molecular orbitals out of these 6 p orbitals. Now, the key theory question that we need to answer is, what are the energies of these molecular orbitals? Which ones are filled? Which ones are empty? And an easy way to do this is to use something called Frost's circle to determine the molecular orbital picture. So in 1,3-butadiene, all 4 molecular orbitals had different energies. In linear 1,3,5-hexatriene, all 6 molecular orbitals have different energies. Is this also true for benzene? Well, what Frost's circle tells us to do is to draw a regular polygon of the size that you want. So in this case, it's going to be a hexagon because it's a 6-membered ring, and place a corner at the bottom. When Frost originally developed this, he put a circle around the hexagon, so that's why it is called Frost's circle. But the circle is actually not necessary for being able to do this diagram. So then, if you just look at where each carbon atom is in the structure of your polygon, you simply draw a line corresponding to molecular orbitals at the location of each carbon atom. So what that means is that we have 4 different energy levels for the 6 molecular orbitals. Psi1 is going to have the lowest energy, but then there are 2 orbitals, Psi2 and Psi3, that are strictly degenerate. They have the same energy. Above that are 2 more molecular orbitals, Psi4 and Psi5, that have the same energy. And then finally, Psi6 is going to be the highest energy molecular orbital. Then what we normally do in a diagram like this is actually place a dashed line halfway up that divides the lower energy bonding orbitals from the higher energy anti-bonding orbitals. There will be some molecules that may have non-bonding orbitals. As we will see, benzene is not one of them. All of the orbitals in benzene are either bonding or anti-bonding. So, how many electrons do we have? Well, because there are 6 p orbitals, there are going to be 6 electrons that will be contributed to the molecular orbitals. the 3 bonding molecular orbitals are all filled and the 3 anti-bonding molecular orbitals are empty. That is indicating that there are 3 pi bonds, which is what we would expect. But molecular orbital theory allows us to delocalize those pi bonds over the entire molecule rather than keep them localized specifically between 2 carbon atoms. Finally, I would like to show you the pictures of these molecular orbitals. Okay, so the 3 bonding molecular orbitals are going to be lower in energy than that of an isolated p orbital. And psi1, as you can see, just like the lowest energy molecular orbital of 1,3-butadiene, is bonding everywhere. Okay, so you have all your blues overlapping with your blues, you have all your reds on top overlapping with your reds, and that shows that there is in fact pi bonding between all 6 carbon atoms. The remaining structures of psi2, 3, 4, and 5 are less easy to derive. I would not expect you at this level to be able to see that the structures look that way, but what is important about psi2 and psi3 is that they each contain 1 node, where the nodes are a plane. Okay, so for psi2, the plane is, a vertical plane. For psi3, the plane is another vertical plane, but it's perpendicular to the vertical plane of psi2. Both of those having 1 node are higher in energy than psi1 is. But again, if you look at these structures, there is a level of symmetry associated with them that is basically bilateral symmetry and not trigonal symmetry. There is nothing in this molecular orbital diagram that suggests the alternating single and double bonds, which would actually be a trigonally symmetric structure. The only other thing I want you to take out of this picture is that the highest energy orbital, psi6, is anti-bonding everywhere. In all cases, the p orbitals are combining out of phase, and therefore you have 3 nodes. Psi4 and psi5 have 2 nodes. What makes this structure, these pictures a little more difficult than what we saw with butadiene is in some of these cases, the nodes actually go through atoms, which is something that's just a little bit more difficult to handle. Okay, so that's your molecular orbital picture, and the fact that all of your bonding molecular orbitals are filled with the 6 electrons, all of your anti-bonding molecular orbitals are empty, and the fact that in an aromatic system you have this especially stable psi1, that if you broke the aromaticity, you would lose that stable psi1. That explains the extra special stability associated with the benzene molecule. So, as I've said, there are many molecules other than benzene that are aromatic, and what we need to do next is start to consider, if we look at a structure of a molecule, can we tell whether it's going to be aromatic or not without actually having to construct a molecular orbital diagram? And we'll do that by looking at something called Huckel's rule.